Here we have some visual examples of elements, mixtures, compounds, and molecules. Okay? So the atoms are represented by single spheres or circles. Okay? Elements of the same size and color are atoms of the same element. So here we have a bunch of individual green dots, right? They're not touching each other, they're just one dot all by itself. So these are atoms, and all of them are green, so you have several atoms of one element. Let's say this is hydrogen. So you have approximately 13 atoms of hydrogen right here. Then we have a purple element right here. We'll say this is oxygen, but you see you have two dots that are touching, two dots that are bonded together. So this is O2. You have molecules of oxygen. Okay, and in each molecule there are two atoms here. So this is one group, but I have two atoms in that group, two atoms in this group. So we have 1, 2, 3, 4, 5, 6, 7, 8 molecules of O2 right here. When we talk about mixtures, you see two different elements in the same container, but they're not bonded together. This green and orange, they're not touching. There's no evidence of a chemical bond here. They're just mixed together. So hypothetically, if I wanted to, I could pick out all of these green dots and separate the orange and the green without using chemical means. Without using a chemical reaction, I can very easily separate the orange and the green dots. The same here. Right here they mixed hydrogen and oxygen, because I'm going to keep using the examples from above. But the green and the purple are not chemically bonded together. So you have a molecule of O2 and you have a bunch of hydrogen atoms, but they're not bonded together. They're just mixed. So if I wanted to, I could separate them. I could just pick out all of the green beads. Okay? And here we have molecules of an element in this box. So we have, let's say this is carbon and this is oxygen. So we have O2 and C2. We have a mixture of two different elements. Okay? But you have more than one atom bonded together of the same element. This is a molecule. We have one group here, one group here, one group here. We have a bunch of groups of these elements. Okay, so this is a mixture of molecules. And then right here, you can see a compound. You have green bonded with two pink beads. So you have two different elements bonded together. Okay, so in this image, you have 1, 2, 3, 4, 5, 6, 7 molecules of this green and pink compound. Here's the compound. In this picture, you have 7 molecules of it. And then of the pink beads by themselves, this element, you have 1, 2, 3, 4, 5, 6, 7 molecules of this element. So you have 7 groups of this element and 7 groups of this compound in this image. Okay? So an element is a pure substance. It is just itself. So this is an element and this is an element. This is just an element of the green and this is just an element of the purple. But when you have more than one of the same element or different elements, when you have more than one, it becomes a molecule. Okay, so this is one molecule, this is one molecule. When there is a chemical bond, when an element is bonded with anything, it is a molecule. When it's bonded with something different, it's a molecule and a compound. Okay, so here we have an element bonded with itself. There's 2 of the same colored dot. That is a molecule of this element. And here we have a green bonded with pink. It is a molecule of that compound because there's 2 different bonded together. Okay? All right. So now this is what we really have been talking about, chemical formulas. a symbolic representation of a chemical compound. So we use our chemical symbols and numbers to represent those nice little pretty dots. Chemical formulas are used to identify substances and determine the number of atoms, which is what we've been doing. The elements present in a compound are identified with the chemical symbol, which is always going to start with a capital letter, and sometimes there will have a little letter. So this is one element, this is one element, and this is a third element. If more than one atom of an element, like here, then you have a subscript. So there are 2 atoms of sodium, so we put a subscript there. There are 4 atoms of oxygen. When we don't have more than one, we don't write a subscript. So when there is only 1 atom, we write the chemical symbol. Okay, and so here, like glucose, that's a type of sugar and your body makes it naturally. This is the chemical formula for glucose. It has 6 carbons, 12 hydrogens, and 6 oxygens. Subscripts versus coefficients, okay? Subscripts are the small numbers behind the element. It shows the number of atoms in each substance. So this example, NH3, how many atoms are there for each element? For this first example, NH3, how many atoms are there for each element? All right, so another example is we have NaCl. Remember, if we don't have a subscript, it means that there is only one. So there's 1 atom of sodium, 1 atom of chlorine. This is the chemical formula for hydrogen peroxide. Okay, and hydrogen peroxide has 2 atoms of hydrogen and 2 atoms of oxygen. And then for coefficients, it's the big number in the front of the formula, and it applies to the entire formula because it shows you the number of molecules. So you have to distribute your coefficient to all elements. So this 2 gets distributed to the nitrogen and to the hydrogen. So now for this example, since we have 2 molecules of this, there are 8 total atoms, okay? Because you have 2 nitrogens, and then 2 times 3 means we have 6 hydrogens. So there are 8 total. For NaCl, we distribute this 3. 3 times the invisible 1 is 3. Distribute 3 to chlorine times the invisible 1 is 3. So you have 6 total atoms, 3 sodiums and 3 chlorines total, because you have 3 groups of NaCl. And this is saying that there are 4 groups, 4 molecules of H2O2. Okay? So here is a practice example. We have a diagram up at the top, and it shows you the evolution of this. So we have 1 molecule of water. There's no coefficient in front of this example, so we know that there is 1, and here's a picture. And in the picture, you have 2 hydrogen atoms and 1 O atom. Now we put a coefficient in front. There are 2 groups of water. 1, 2. So when you count the hydrogens total, you have 1, 2, 3, 4, and then you have 2 oxygens. Okay, and then you have 1 molecule of hydrogen peroxide, where you only have 2 hydrogens and 2 oxygens. 2SO3. What are the elements? How many atoms? How many molecules? So we have sulfur, which is the capital S, and oxygen, which is the capital O. How many atoms are in this compound? So remember, when we have a coefficient, we have to distribute it. 2 times the invisible 1 for sulfur means there's 2 total atoms for sulfur. 2 times the 3 for oxygen, we distribute the 2 to the 3, and when we distribute, we multiply, means we have 6 total atoms for oxygen. So 6 total atoms for oxygen and 2 total atoms for sulfur gives us 8 total atoms. How many molecules of the compound are there? Our coefficient tells us the number of molecules. So we have 2 molecules of SO3, 2 groups of this compound, okay? Okay, H2O, how many molecules do we have in H2O right here? Is there a coefficient? So I have 3 molecules of sodium sulfate. This big number in front of our chemical formula tells me I have 3 groups of this compound. Okay? Glucose, there are 24 total atoms, and there is no there is no coefficient, so we have 1 molecule. Methane, what are the total number of atoms? 4 plus 1 gives us 5 total atoms. And then the last example is hydrochloric acid. How many molecules do we have of this last example? Sorry, of 2HCl. How many molecules? All right, so there are 2 molecules of HCl.